Most people recognize the name Boeing. It is synonymous with air travel itself. For decades, this American aerospace giant has shaped the very way we connect our world. Its aircraft are the workhorses of global commerce and tourism, crisscrossing continents and oceans every minute of every day. When you board a flight, there is a very good chance you are stepping onto a machine designed and built by Boeing. The sheer scale of its operation is difficult to comprehend. Thousands of its planes are in the air at any given moment, forming an invisible high-altitude circulatory system for the planet. This global presence makes Boeing not just a company, but a fundamental part of modern infrastructure. The impact of Boeing extends far beyond just manufacturing airplanes. The company's designs have driven innovation across the entire aviation industry, from engine efficiency to air traffic control systems. Think of the iconic Boeing 747, the Queen of the Skies, which democratized long-haul travel for millions. Or consider the modern 787 Dreamliner, which introduced a new era of fuel efficiency and passenger comfort. These are not merely modes of transport. They are technological marvels, the culmination of millions of hours of design, engineering, and testing. Their existence has reshaped economies, enabled global business, and allowed families to reunite from opposite ends of the earth. The world is a smaller, more accessible place because of these flying machines. Understanding a Boeing plane is to understand a complex ecosystem. It is a fusion of raw power, delicate electronics, advanced materials, and human expertise. For passengers, the experience might be defined by the comfort of a seat or the quality of the in-flight entertainment. For airlines, it is a question of reliability, efficiency, and cost. For pilots and crew, it is a trusted tool, a sophisticated office in the sky. All these perspectives converge into a single flying object that weighs hundreds of tons yet soars gracefully at 35,000 feet. The story of a Boeing is the story of modern aviation itself, with all its triumphs and its challenges. This exploration will take you beyond the cabin window and into the heart of these incredible machines. We will look at what makes them comfortable, what keeps them safe, and how they are designed to endure decades of service. We will examine the intricate systems that pilots rely on and the procedures that cabin crews follow to ensure your well-being. We will also confront the difficult realities of aviation accidents, understanding what went wrong and what lessons were learned. Flying is a partnership between technology and people, and this journey will explain the roles both play in making air travel one of the safest forms of transportation ever conceived by humankind. When you settle in for a flight, your immediate world shrinks to the space around your seat. Boeing has invested enormous resources into making that small space as pleasant as possible. One of the most significant yet invisible features is the cabin air system. Many passengers worry about stale air, but the reality is quite different. The air in a Boeing cabin is a carefully controlled mixture of fresh air from outside and recirculated air that has been passed through hospital-grade HEPA filters. These filters are extremely effective, capturing over 99.9% of airborne microbes, dust, and allergens. The entire volume of cabin air is completely refreshed every 2 to 3 minutes, ensuring a quality that often surpasses what you breathe in an office or a mall. Passenger comfort is also directly tied to cabin architecture and seating. Newer models like the Boeing 787 Dreamliner feature higher ceilings and larger electronically dimmable windows, creating a sense of openness and reducing claustrophobia. The 787 is also designed to have a lower cabin altitude, pressurized to the equivalent of 6,000 feet instead of the typical 8,000 feet. This subtle change means more oxygen and higher humidity in the air, which helps reduce symptoms of jet lag like fatigue and headaches. Seating design itself is a science, balancing ergonomics, weight, and durability. While airlines ultimately choose the specific seat models and their spacing, Boeing provides the foundational cabin structure that makes modern, slimline seats with built-in entertainment systems possible. In-flight entertainment and connectivity have become standard expectations, and Boeing integrates these systems deep into the aircraft's design. The latest cabins are wired to support high-definition seatback screens, on-demand movies, satellite Wi-Fi, and USB charging ports at every seat. This requires a complex network of wiring and servers that must be seamlessly integrated without interfering with the plane's critical flight systems. The goal is to provide a connected experience that mirrors life on the ground. From streaming a movie to sending an email, These features transform the cabin from a simple mode of transport into a multifunctional space for work or leisure, making long-haul flights far more manageable for passengers. Finally, the quality of the ride itself is a key component of comfort. Boeing uses advanced aerodynamics and flight control systems to mitigate the effects of turbulence. While bumps are an unavoidable part of flying, the aircraft's wings are designed to flex and absorb much of the energy. Autopilot systems can also make tiny, constant adjustments to maintain a smooth flight path. Furthermore, the engines on modern Boeing jets, like the GNX on the 787 or the LEAP-1B on the 737 MAX, are significantly quieter than their predecessors. This reduction in engine noise, combined with better cabin insulation, creates a more serene and less fatiguing environment for everyone on board. For passengers, reliability often means one simple thing: your flight departs and arrives on time without any drama. This is the end result of a much deeper, more complex definition of reliability that airlines and manufacturers live by. For an airline, reliability is a key financial metric. An aircraft that is grounded for unscheduled maintenance is an aircraft that is not generating revenue. Therefore, they look for planes that can consistently fly their scheduled routes with minimal downtime. This is measured by something called dispatch reliability, which is the percentage of flights that depart without a technical delay. Major Boeing models like the 777 and 737 NG routinely achieve dispatch reliability rates above 99%, a testament to their robust engineering. This high level of reliability is not an accident. It is designed into the aircraft from the very beginning. The principle of redundancy is at the core of this philosophy. Every critical system on a Boeing plane has at least one backup, and often two or three. For example, there are multiple hydraulic systems, electrical generators, and flight computers. If one system fails, another seamlessly takes over without any interruption to the flight's safety. This multi-layered approach ensures that a single point of failure can almost never lead to a catastrophic situation. The aircraft is designed to tolerate failures and continue operating safely until it can be repaired on the ground. Reliability is also maintained through a rigorous and continuous maintenance schedule. These are not like cars that you take to the mechanic only when something breaks. Aircraft undergo constant checks. There are daily inspections, more detailed weekly checks, and heavy C checks and D checks that can take the plane out of service for weeks at a time. During these major overhauls, the aircraft is systematically taken apart, inspected, and rebuilt. Parts are replaced not when they fail, but long before they are expected to, based on a meticulously calculated lifespan. This proactive approach is fundamental to keeping the fleet safe and dependable over many years of service. Finally, the global support network that Boeing provides is a crucial part of the reliability equation. When an aircraft does have a technical issue at an airport far from its home base, the airline needs access to spare parts and technical expertise quickly. Boeing maintains a massive global logistics network to ensure that a replacement part, whether it's a simple sensor or a major engine component, can be flown in and installed with minimal delay. This worldwide support system is just as important as the design of the plane itself in keeping the global fleet flying reliably day in and day out. A commercial airliner is one of the most durable machines ever built. Unlike a car, a Boeing jet is not designed to be used for a few years and then discarded. Its operational life is measured not in years, but in flight cycles. A single flight cycle consists of one takeoff and one landing. These events place the most stress on the airframe, particularly through the pressurization and depressurization of the fuselage. The aluminum skin of the aircraft expands slightly as it climbs to altitude and contracts as it descends. Over thousands of repetitions, this can cause metal fatigue. A typical Boeing 737 is designed to withstand around 75,000 flight cycles, while a long-haul jet like the 777 might be designed for around 60,000 cycles. The actual number of years a plane stays in service depends heavily on how it is used. An aircraft used for short-haul flights will accumulate cycles much faster than one used for long-haul intercontinental routes. For example, a 737 flying multiple one-hour flights a day might reach its cycle limit in 25 to 30 years. In contrast, a 777 flying 12-hour routes might take much longer to reach its cycle limit, potentially staying in service for a similar number of years, but with fewer total takeoffs and landings. Economics also plays a huge role. As an aircraft ages, its maintenance costs increase, and its fuel efficiency may be lower than newer models. Airlines will often retire a plane when it is no longer economically viable, even if it has not reached its structural life limit. The longevity of a Boeing jet is a direct result of the materials used and the stringent maintenance it receives. The airframe is primarily constructed from high-strength aluminum alloys, chosen for their durability and resistance to corrosion. As the plane goes through its heavy maintenance checks, its structure is meticulously inspected for any signs of fatigue or corrosion using techniques like ultrasound and X-rays. Any detected issues are repaired immediately. This continuous process of inspection and repair essentially rejuvenates the airframe, allowing it to safely continue flying for decades. It is not uncommon for a well-maintained jetliner to serve with multiple airlines over its lifespan before finally being retired. When a Boeing plane is finally retired from passenger service, its journey is often not over. Many older passenger jets like the 747, 767, and 757 find a second life as cargo freighters. Their strong airframes and large capacity make them ideal for hauling freight around the world. Converting a passenger plane to a freighter involves stripping out the cabin, reinforcing the floor, and installing a large cargo door. This allows the aircraft to continue generating value for many more years. Only after its useful life as a freighter is over will it be flown to an aircraft boneyard, typically in a dry desert location, where it will be stripped for valuable spare parts before the remaining fuselage is recycled. Modern Boeing aircraft are defined by the advanced technology that makes them safer, more efficient, and honestly, just easier to fly. A key innovation has been the increasing use of composite materials. The Boeing 787 Dreamliner, for instance, is the first major airliner to have a fuselage and wings made primarily from carbon fiber reinforced plastic. These composites are incredibly strong and durable, yet significantly lighter than aluminum. This weight reduction is a primary driver of the 787's remarkable fuel efficiency. Composites also do not corrode like metal, which can reduce long-term maintenance costs. Furthermore, their strength allows for the creation of more complex and aerodynamically efficient shapes, such as the elegantly curved wings of the 787. In the cockpit, the revolution has been just as profound. The old dashboard of countless analog dials and gauges has been replaced by a glass cockpit. This consists of several large liquid crystal display screens that present flight information to the pilots in a clear, intuitive, and customizable format. These displays integrate data from numerous sensors around the aircraft, showing everything from airspeed and altitude to engine performance and navigation maps. This allows pilots to have much better situational awareness. Advanced avionics systems like the fly-by-wire controls on the 777 and 787 translate pilot inputs into electronic signals, which are then used by computers to move the control surfaces. This system can prevent the pilot from making maneuvers that would exceed the plane's structural limits, adding a critical layer of safety. Safety is further enhanced by an array of automated monitoring and warning systems. The Enhanced Ground Proximity Warning System, or EGPWS, uses a GPS database of the world's terrain to warn pilots if they are flying dangerously close to the ground or an obstacle. The Traffic Collision Avoidance System, or TCAS, communicates with other nearby aircraft, providing pilots with alerts and coordinated instructions to avoid mid-air collisions. These systems work in the background, constantly monitoring the flight environment and providing a crucial safety net. They are designed to prevent accidents long before a dangerous situation can fully develop, acting as an electronic co-pilot that never gets distracted. Efficiency is not just about materials, it's also about the brain of the aircraft. The Flight Management System, or FMS, is a sophisticated onboard computer that automates many of the tasks of managing a flight. Before takeoff, pilots program the entire route into the FMS. During the flight, the FMS can control the autopilot to fly the most fuel-efficient route, calculate the optimal altitude and speed, and manage the aircraft's vertical profile for descent and landing. By continuously optimizing the flight path, the FMS saves significant amounts of fuel over the course of a year, which translates into lower costs for airlines and a reduced environmental footprint for aviation. Passenger safety on a Boeing aircraft is a comprehensive system that extends far beyond the reinforced cockpit door. It begins with the fundamental design of the cabin itself. Seats are engineered to withstand immense G-forces, and the materials used in the cabin interior, from carpets to sidewall panels, are fire retardant and designed to emit minimal smoke and toxic fumes in the event of a fire. The placement of emergency exits is carefully calculated to allow for a full evacuation of the aircraft in 90 seconds or less, even if half the exits are blocked. This 90-second rule is a certification standard that dictates the number and location of exits on every airliner. The aircraft is equipped with a wide range of emergency equipment for various scenarios. Above your seat, oxygen masks are ready to deploy automatically if the cabin pressure drops. These are connected to chemical oxygen generators that provide about 12 to 15 minutes of breathable air, more than enough time for the pilots to descend to a safe altitude where supplemental oxygen is no longer needed. Life vests are typically stowed under or between your seats for the highly unlikely event of a water landing. Additionally, the cabin is equipped with multiple fire extinguishers, first aid kits, and automated external defibrillators to handle medical emergencies. Flight crews are extensively trained to handle a wide variety of in-flight emergencies, including medical situations. Cabin crew members are not just there to serve drinks, they are certified safety professionals. They receive rigorous initial and recurrent training in first aid, CPR, and the use of the onboard medical equipment like the AED. If a passenger experiences a serious medical issue, the crew's first response is to provide immediate care and assess the situation. They can also use a satellite phone to contact a ground-based medical support service, like MedAir or StatMD, which connects them with an emergency room physician for real-time guidance and advice. Based on the medical advice and the passenger's condition, the captain will make the final decision on how to proceed. If the situation is life-threatening, the flight will divert to the nearest suitable airport to get the person to a hospital. This decision is not taken lightly, as a diversion can be costly and disruptive, but the health and safety of the passenger is always the top priority. The flight crew, ground-based doctors, and air traffic control will coordinate to make the diversion as quick and efficient as possible, ensuring that the aircraft can land and be met by emergency medical services on the ground. While modern aircraft are incredibly reliable, minor technical issues can and do occur. These are almost always non-events from a safety perspective, thanks to the layers of redundancy built into the plane. For example, a passenger might notice a flickering reading light or an in-flight entertainment screen that won't turn on. While inconvenient, these are isolated electrical issues within the cabin and have no connection to the aircraft's critical flight systems. The cabin crew will typically try to reset the system, and if that doesn't work, they will make a note for maintenance to fix it on the ground. The pilots are often not even aware of such minor cabin issues. More significant, but still manageable, failures might involve a non-critical system that the pilots do monitor. For instance, one of the plane's several weather radar systems might fail. The pilots would receive an alert on their display, but they would simply continue the flight using the remaining fully functional radar systems. Another example could be a fault in a single brake unit within the landing gear. The aircraft has multiple brakes on each main gear, and the loss of one would be compensated for by the others. The pilots would be alerted, might plan for a slightly longer landing roll, and would inform maintenance so the unit could be replaced after landing. The process for handling these events is highly standardized. When a fault occurs, an electronic message is sent to the flight deck displays via the aircraft's central monitoring system. This message will tell the pilots exactly what has failed and will often reference a specific procedure in their Quick Reference Handbook. This handbook contains checklists for virtually every conceivable non-normal situation. The pilots will methodically work through the checklist, which ensures they take the correct steps to manage the failure and secure the affected system. This procedural approach removes guesswork and ensures a consistent and safe response every time. Once the aircraft is on the ground, the rectification process begins. The pilots will log the failure in the aircraft's technical logbook. This log is a legal document that communicates the plane's status to the maintenance team. A certified aircraft maintenance engineer will then troubleshoot the issue using the fault code from the aircraft's computers as a starting point. They will consult the aircraft's maintenance manuals, which provide detailed repair procedures. Once the faulty component is identified, it is replaced, the system is tested, and the engineer signs off on the repair in the logbook. The aircraft is not permitted to fly again until the issue is fully resolved and certified as airworthy. Despite an outstanding overall safety record, commercial aviation is not immune to tragedy. Boeing, as a manufacturer with tens of thousands of aircraft delivered over many decades, has had its share of major accidents. Statistics show that air travel is remarkably safe, with the accident rate being fractions of a percent per million flights. However, the sheer loss of life in a single crash can have a profound impact on public perception and the industry itself. For instance, the crash of Japan Airlines Flight 123 in 1985, a Boeing 747, resulted in 520 fatalities. The cause was traced back to a faulty repair performed by Boeing technicians years earlier, which led to a catastrophic structural failure of the rear pressure bulkhead. More recently, the two crashes involving the Boeing 737 MAX, Lion Air Flight 610 in 2018, and Ethiopian Airlines Flight 302 in 2019, shook the industry to its core. These two accidents resulted in the loss of 346 lives and led to the worldwide grounding of the entire 737 MAX fleet for nearly 2 years. The investigation revealed that a new flight control system, known as the Maneuvering Characteristics Augmentation System, or MCAS, was a key contributing factor. The system, designed to compensate for the aerodynamic effects of the plane's larger engines, was repeatedly activated by a single faulty sensor, pushing the nose of the aircraft down despite the pilot's efforts to counteract it. The impact of such accidents extends far beyond the tragic loss of life. The property damage is immense, with the value of a modern jetliner often exceeding $100 million. The subsequent investigations, lawsuits, and regulatory actions can cost the manufacturer and airlines billions. The 737 MAX grounding, for example, cost Boeing over $20 billion in direct costs, including compensation to airlines and production halts. More importantly, these events cause deep damage to the company's reputation and to the public's trust in the safety of air travel. Rebuilding that trust is a long and arduous process that requires transparency, accountability, and demonstrable improvements in safety. Every major accident undergoes an exhaustive investigation, typically led by the government agency of the country where the crash occurred, such as the National Transportation Safety Board in the United States. Investigators meticulously recover and analyze the wreckage, study the flight data and cockpit voice recorders, the so-called black boxes, and interview witnesses. The goal is not to assign blame, but to determine the probable cause and contributing factors. The final report often includes urgent safety recommendations for the manufacturer, airlines, and regulators to prevent a similar accident from ever happening again. These painful lessons are what drive continuous safety improvements across the entire industry. For every accident that occurs, there are, honestly, countless other incidents where disaster was skillfully averted. These near misses often provide equally valuable lessons. One of the most famous examples is United Airlines Flight 232 in 1989. The DC-10, an aircraft built by McDonnell Douglas, which later merged with Boeing, suffered a catastrophic failure of its tail-mounted engine, which severed all of its hydraulic lines, rendering the flight controls useless. The crew, led by Captain Al Haynes, discovered they could exert some directional control by varying the thrust of the two remaining wing-mounted engines. Through incredible teamwork and ingenuity, they managed to guide the crippled jet to a crash landing in Sioux City, Iowa. While 112 people died, 184 survived an event that really should have been unsurvivable. Technology has also played a critical role in preventing accidents. The Traffic Collision Avoidance System, or TCAS, has been credited with preventing numerous mid-air collisions. A notable case occurred over Germany in 2002, though it ended in tragedy due to conflicting instructions. A Bashkirian Airlines Tupolev and a DHL Boeing 757 were on a collision course. The TCAS on the 757 issued a descend command to its pilots, while the Tupolev pilots received a climb command from air traffic control. The Tupolev pilots followed the controller, while the 757 pilots followed their TCAS, and both planes descended, leading to a collision. This tragic event reinforced a critical rule that is now standard procedure worldwide. A pilot must always obey a TCAS resolution advisory, even if it contradicts an instruction from air traffic control. The development of Enhanced Ground Proximity Warning Systems, or EGPWS, was a direct response to a series of controlled flight into terrain accidents, where perfectly good aircraft were flown into mountains or the ground, often in poor visibility. A tragic example was the 1995 crash of American Airlines Flight 965, a Boeing 757, into a mountain in Colombia. The crew had become disoriented while navigating towards Cali. Today's EGPWS uses a detailed terrain database and GPS to provide pilots with clear early warnings like terrain, pull up. This technology has virtually eliminated CFIT accidents for aircraft equipped with it, saving thousands of lives. Sometimes averting disaster comes down to a combination of robust design and quick thinking. In 2010, Qantas Flight 32, an Airbus A380, not a Boeing, suffered an uncontained engine failure that sent shrapnel tearing through the wing, damaging fuel, hydraulic, and electrical systems. The flight crew spent nearly 2 hours in the cockpit, working through a cascade of 54 error messages to understand the state of their crippled aircraft before successfully making an emergency landing in Singapore. The incident highlighted the importance of crew training in handling complex, unforeseen failures and the resilience that is built into modern airliners, which are designed to sustain significant damage and still remain flyable. While technology has made flying incredibly safe, aircraft are still operated and maintained by human beings, and, well, humans are fallible. A significant portion of aviation incidents and accidents have human error as a contributing factor. This can occur in the cockpit, in the maintenance hangar, or even on the design floor. Pilot error can involve misinterpreting an instrument, making a poor navigational decision, or failing to follow standard operating procedures. For example, the crash of Air France Flight 447 in 2009 was ultimately caused by the pilot's inappropriate control inputs after the autopilot disconnected due to iced-up speed sensors, leading to an aerodynamic stall from which they did not recover. Engineering and maintenance mistakes can introduce hidden dangers that may not become apparent until much later. The aforementioned crash of Japan Airlines Flight 123 was the direct result of an improper repair to the rear pressure bulkhead 7 years earlier. The maintenance team used a single reinforcing plate with 1 row of rivets where 2 plates with 2 rows were required, significantly weakening the structure. Over thousands of pressurization cycles, the weakened repair failed, leading to an explosive decompression and the loss of the vertical stabilizer. This highlighted the critical importance of adhering strictly to approved repair schemes and the need for multiple layers of inspection and quality control. Even cabin crew actions, or inactions, can contribute to negative outcomes, though rarely to the accident itself. Their primary role is safety, and a failure to properly secure the cabin for takeoff or landing, or to effectively manage an emergency evacuation, can worsen the consequences of an incident. This is why their training is so rigorous and repetitive. They practice emergency procedures over and over so that their response becomes automatic, even under the extreme stress of a real crisis. The goal of the entire system, from pilot training to maintenance protocols, is to minimize the opportunities for human error and to build in safeguards that can catch mistakes before they become catastrophic. Recognizing the inevitability of human error, the aviation industry has shifted its focus from trying to eliminate it entirely to managing it. This approach is known as Crew Resource Management, or CRM. CRM training emphasizes teamwork, clear communication, and cross-checking in the cockpit. It encourages junior crew members to speak up if they see a senior pilot making a mistake, breaking down the traditional hierarchy. It treats the flight crew as a team dedicated to managing the flight safely, using all available resources: people, technology, and information. This philosophy has been credited with preventing countless accidents by creating a more collaborative and error-tolerant cockpit environment. The safety demonstration performed by the cabin crew before every takeoff is a familiar ritual for most travelers. It can be easy to tune out, especially for frequent flyers. However, every piece of information presented is critical and could be life-saving in an emergency. The briefing begins by asking for your attention and instructing you to follow along with the safety card in your seat pocket. This card provides visual, step-by-step instructions that reinforce what the crew is demonstrating. It is tailored to the specific aircraft type you are on, which is important because details like exit locations can vary between, for example, a Boeing 737 and a Boeing 777. The first key instruction concerns your seatbelt. The crew will demonstrate how to fasten, tighten, and release it. They will emphasize that it must be worn low and tight across your hips whenever the seatbelt sign is on. This is not just for turbulence. It is crucial for your safety in the event of a sudden, unexpected jolt or a rejected takeoff. Keeping the belt fastened even when the sign is off is a good practice. The briefing will then point out the emergency exits, highlighting the ones nearest to your seat. You are instructed to count the number of rows to your nearest exit, so you could find it in the dark or in a smoke-filled cabin. The next part of the demonstration covers the use of the oxygen masks. The crew explains that if cabin pressure is lost, panels overhead will open and masks will drop down. You are instructed to pull the mask firmly towards you to start the flow of oxygen and to place it over your nose and mouth. Crucially, they stress the importance of securing your own mask before helping others, including children. This is because the lack of oxygen at high altitude can incapacitate you in a matter of seconds. You cannot help anyone if you are unconscious. The life vest demonstration follows, showing you where it is located and how to put it on, but with the critical warning not to inflate it until you are outside the aircraft, as an inflated vest could trap you inside a sinking cabin. Finally, the briefing covers other important items. It will remind you that smoking and tampering with smoke detectors are prohibited by law. It will also detail the restrictions on the use of personal electronic devices, explaining when they must be switched to airplane mode or turned off completely, particularly during takeoff and landing, to prevent any potential interference with the aircraft's navigation and communication systems. The crew concludes by reminding you to review the safety card and asking you to alert them to any questions or concerns. This entire presentation is a carefully scripted and regulated safety procedure, designed to give every passenger the essential knowledge they need to protect themselves. The intricate dance of technology, procedure, and human expertise that gets a Boeing jetliner safely from one city to another is one of the great triumphs of modern engineering. From the composite materials that make the plane lighter and stronger, to the redundant systems that provide multiple layers of protection, every component is designed with safety as its ultimate purpose. The pilots in the cockpit and the maintenance crews on the ground are part of a global system built on decades of experience, learning from both successes and failures. The result is a mode of transportation that has achieved a level of safety that would have been unimaginable to earlier generations. However, the safety chain is not complete without the final link, the passenger. Your awareness and preparedness are a vital part of the system. While the probability of being in a serious aircraft emergency is incredibly small, your actions during those critical moments can make a significant difference. Paying attention to the safety briefing is not just a matter of courtesy, it is a matter of personal responsibility. Knowing how to operate your seatbelt, where your nearest exit is, and how to use the oxygen mask and life vest are fundamental skills that you might one day need. It is information that costs you nothing but a few minutes of your attention. The next time you are on a flight and the cabin crew begins their demonstration, take a moment to watch and listen. Put down your phone, pause your conversation, and locate the safety card. Think of it as a small insurance policy. You hope you will never need it, but you will be profoundly grateful for it if you do. The crew is not performing for their own benefit. They are fulfilling their most important duty, which is to prepare you for the unlikely event that something goes wrong. They are your first responders in the sky, and the information they provide is your first line of defense. Ultimately, flying is a partnership. Boeing builds a safe plane, the airline maintains it, the crew operates it professionally, and you, the passenger, play your part by being informed and attentive. By understanding the basics of aircraft safety and respecting the procedures that have been put in place, you contribute to the collective well-being of everyone on board. So, buckle up, listen to the briefing, and rest assured that you are on one of the safest machines ever created, supported by a global team dedicated to getting you to your destination securely.